For this particular video, we're going to take a look at logarithmic functions. We're going to graph logarithmic functions and then graph them also using transformations. So if we have to add something here, subtract something there, what kind of transformation does it do to the parent function of a log? So for this one, we've got the expression of f of x is equal to 1/2 log base 2 of x plus 1 in parentheses and then plus 2. So let's talk about what kind of transformations do we see based off of what the equation is. All right. So we know, excuse me, that this 1/2 on the outside means that it's going to be a vertical compression. So we'll write that in here. So let me get the color that you can actually see. All right. So the vertical compression. And then noticing that there's no sign in the front here, that means it's going to still go in its normal fashion. We don't have a reflection about the x-axis. Looking in here, we do not have a reflection about the y-axis, because if so, then all of these in here would be negative, meaning that the x would be negative, I should say. This plus 1 means that we have a left-right shift. And in this case, since it's plus 1, that means we move left 1. And then at the very end, we have plus 2, which then means we take the entire graph and we move it up 2 units. So all points we would normally have had, that moves them up 2 units. All right, so let's choose some values so that we can go ahead and graph this. So when we deal with logs, it's a little different than what we would do normally. I have to make sure that what I have here is something that is a multiple of 2. And when I talk about multiple of 2, like 2 to some power. All right. So just to refresh our memory, if we had log base 2 of 2, well, that's 1. Log base 2 of 4. So what that means is we're taking. The job of the log is to figure out what the exponent would be. So log base 2 of 4. So that means it's the same as log base 2 of 2 squared. So that 2 will come out, remembering from the logarithmic properties. So we have 2 log base 2 of 2. And then log base 2 of 2 is 1. So that means I have 2 times 1, right, which is going to give me 2. So the job is to figure out the exponent. That's what a log does. All right, so now let's go back to here. I'm going to need numbers in here that are, some kind of product with 2. It's 2 times 2 times 2 times 2, something along those lines. So then the first number I want to choose is I'm going to go through and choose, to get something that works right, I'm just going to use 1. So if x is 1, then I get 1 plus 1, which is 2. Log base 2 of 2 is 1. I have then half of that, so it gives me 1/2. 1/2 plus 2 is 2.5. All right, so let's choose another number that will give me something that is a multiple of 2. So if I choose 3 for my x, 3 plus 1 is going to give me 4. Log base 2 of 4 is just like we did over here. Log base 2 of 4 is equal to log base 2 of 2 squared. The 2 then comes out to the front, and then I have log base 2 of 2, and that becomes 1. So now we have this value here is going to be 2. 2 times 1/2 is 1. 1 plus the 2, that gives me 3. Now I want to choose another number. So then here, if I have an 8 here, so I'm going to just do a little math here. So log base 2 of 8. Well, remember that 8 is nothing more than 2 to the 3rd power. So the exponent comes out, and then I have log base 2 of 2. So again, we're at 3. All right, so if I substitute then, in order to get 8, I have to substitute a 7 in for x. So then this will become 3. Half of 3 is 1.5. 1.5 plus 2 will give me 3.5. And let's just plot some of these points so that we get an idea of what's going on here. All right, so if we go through and I look at 1, I'm going to be at 2.5. So 2.5 looks about there. Okay, at 1. And then at 3, I'm going to be at 3. So that should be about there. And then at 7, which I'm way over here, now I'm going to be at 3.5, which looks like there. All right. We've got to figure out now like other values for here. So I'm going to go through and let's see. If I had log base 2 of 1, all right, so let's take a look at this. Log base 2 of 1. All right, so 2 to what power will give me 1? Well, remember, log base anything of 1 is going to give me 0. Okay, so, and it's just like dealing with all of these that I see here, right? If I have, 2 and then log base 2 of 8, 2 to what power is 8? Oh, that's where 3 came from. Go back to over here. 2 to what power gives me 2? Well, that would be an exponent of 1. Looking at this, 2 to what power gives me 4? Well, that's 2. So it's a couple different ways at which to look at it so that you can get the understanding. Okay. So now if I substitute 0 in for x, which would then give me 1, then I'm going to take the log of. So I put 0 in for x. All right, well, then that means this part here is going to be 0. 1/2 times 0 is 0 plus 2. All right. So now, if I'm at 0, I'm up here at 2. So you can see what's happening here. And if we know what goes on with our log functions, we knew for exponentials we had horizontal asymptotes. But with our log functions, we have vertical asymptotes. And the vertical asymptote is told to us based on this information here. All right? So then that means when we said, hey, we moved left 1 unit, normally if we didn't have any kind of left-right shift, my vertical asymptote would be on the y-axis. So now that means that my vertical asymptote is here at -1. So I'm going to try my best to get right through -1. It's close, but you get the idea. So now I'm going to play connect the dots. We're going to just continue our curve this way. And we know that's what that's going to look like. And then remember, this is going to approach the dashed line, but it's never going to intersect it because that is the idea of an asymptote line. So there's what our graph looks like. Okay. Again, the process by which you go through is the same with all the other processes we've gone through with trying to graph something. It's just now we have a couple more things we have to remember. All right, so let's take a look at another example. In this example, it's asking us, okay, figure out the asymptotes, the domain, the range, and describe the end behavior. Now, we've already graphed this. That's what we did in the last example. I just zoomed in a little closer so it was easier to see. And here you can clearly see what our graph does and how we plotted it, and it was exactly the same. So now when we talk about the asymptote, the asymptote is going to be located, it's going to be vertical, and here you can see that it's going to be -1. Now it looks like it actually is touching -1, but again, remember these are getting so close to that vertical asymptote. Each time I move, I'm getting closer and closer to that. So it will never cross it. It's just going to look like it actually is at it. So then in that case, my asymptote is a vertical line at x is equal to -1. My domain, so notice there's nothing over here. So then that means that my domain does not start until I get past this asymptote line. So doing this in interval notation, that means it cannot include -1. So then that means I'm going to have parentheses, -1. And notice it continues in this direction. So it's going to go -1 to infinity. My range, oops, there it goes. My range, well, starting in our negative values. We're moving from the bottom. We're going to move our way up. This is a continuous graph. It's just going to keep going downward. If it was, just with the arrows, it continues this way. This one continues this way. Okay. So this means then, as I'm coming up, yes, I slow down, but I'm still increasing. It's just going to take me longer to get there. So my range actually starts way down here at negative infinity, and it's going to continue forever back in the other direction, so it goes to positive infinity. So now I have to describe the end behavior. Right, so as x approaches infinity, right, as x moves this way, what happens to the graph? Well, when we talked about our range, we see that this continues to infinity. So as x moves to infinity, so does the function. So f of x approaches infinity. As x approaches, and here we got to be careful, all right, as x approaches, in this case, it's coming this way towards -1. There's nothing over here again. So remember that. There's nothing here. So I'm not going to start here and move my way towards x because there's no value there that would make sense. So we actually have to say as x approaches -1 from the positive side. In other words, as I come in this way, what's happening? Because I can't come in from this side. All right? So if we were dealing with rational functions, we would have it, from both sides. We're saying, oh, if I approach from this side, this is this. If I approach from this side, this is something else. So here, we're looking at it as if, okay, well, what happens when we approach from the right-hand side, from the positive direction? Well, as I come in this way, where's my graph going? Well, my graph is moving down. So that means that my function approaches negative infinity. So the key part, the new part, I should say, is right here, where normally we'd say, oh, if I'm coming in from this side, then I have some graph over here, but there is nothing here to graph, nothing to look at. But on this side, as I approach from the positive direction, my graph is continuing to move down from coming in this side. All right. Okay, so we've gone through and we've graphed it. Then we've talked about the transformations. We've talked about how the transformations will move things for our asymptote. It will also change our domain. It's always going to be all real numbers when dealing with the range. We've talked about the end behavior. As x gets large, what happens? As x approaches -1 from the positive direction, what happens to the graph? So these are your general descriptions for log functions. All right, so thank you very much. Hopefully this was helpful, useful, and the like. And subscribe to our Charahoe Pre-Calculus YouTube page if this was useful, and provide us with any feedback you feel is necessary. Have a great rest of your day.